Hi guys, Miss O'Connell here. So I appreciate you, for those of you who did fill out that form yesterday talking about the best part of your spring break. I really do appreciate you sharing all that information with me. It was nice to read, to see that some of us had some time to get outside and to finish some books that we always wanted to read. So it's difficult not seeing you guys, but thank you for those of you who did fill that out and gave me a quick update about your life. Okay, so on the screen right now, you can see the answer key to the review activity that we took a look at in class yesterday. So I used Kami to complete this, but again, whatever application you used or whether you printed it and filled it out is perfectly fine. We just want to do the best we can with the resources that you know how to use. I will never deduct points for something like that. Okay, the goal is to complete the activity. So you might want to pause the video and take a look at your maze and make sure it lines up. Okay, if you have any questions with any of these moves or movements along the path, so let's say that you didn't get 4.97 seconds as the period, please attend extra help. So a reminder, extra help is Tuesdays, Thursdays, and Fridays from 2:30 to 3:15. And tomorrow, again, on Wednesdays, we have mandatory class during our shortened schedule. Okay, that shortened schedule is posted in Google Classroom. Okay, and you will get a reminder about the Google Meet. That will count as a grade. Okay, so your attendance, you have to show up and play the Kahoot. That will, from now on, count as a grade. You must attend class on Wednesday. It's important that I see you at least once a week. Okay, so today we're going to be talking about Hooke's law. We're going to be applying the law in a little bit more depth. So in Classroom, you see the actual copy of the lab. Okay, I'll make a copy for you. Let's talk about the introduction. Okay, some background information about Robert Hooke and who he was and this law. In 1678, Robert Hooke announced the invention of a spring scale. Okay, and in doing so, the relationship for elastic materials is now known as Hooke's law. Think about in class when we have used a spring scale. A spring scale. So we use spring scales in order to measure the mass or the weight of an object in newtons. Okay, so in the invention of Hooke's law, we determined a way to accurately assess the weight and the mass of an object. Right on one side of the spring scale is the measurement in grams. On the opposite side of the spring scale is the measurement in newtons. Okay, and his law states that when an object is acted upon by a force, that object can be compressed, stretched, or bent. When the force is removed, the object returns to its original shape. It is said to be elastic. So you apply a force and remove a force, and the object maintains its original shape. It is an elastic material. Okay, materials that follow generally that law would be things like steel bars, rods, wires, springs, made up of different variations of metals, a diving board, sometimes rubber bands, okay, are considered to be elastic. But the stretch that they experience is directly proportional to the load that they support, meaning the amount of weight that you add to the end directly influences the amount of stretch. Okay, and that's Hooke's law. So the goal of this lab is to investigate the relationship between force applied to a spring and the distance that the spring stretches, okay, which we know is called Hooke's law. We are also going to, the best you can, if you have a hair tie, that works. If you can find a rubber band at home or anything that's made of elastic material, do the best that you can. Okay, so we're just going to give the second part a try. Okay, the first part will be graded. The second part will be graded based on you gave it a shot, okay? And we're gonna focus on the first part of this lab today. We will revisit the second part on Thursday. Okay, so you are at home, but please use common sense and do not shoot the rubber band at pets, siblings, parents, grandparents, etc. Okay, please be careful when you are, if you do locate a rubber band or a hair tie, please be careful testing those out. So the materials that we are going to use a simulation to perform this lab. So it's LinkedIn Classroom. You're going to go to Springs and Masses, or Masses and Springs, the basics. You're going to click play. Once you click play, you're going to head to the lab. My computer is frozen. Okay, there we go. Sorry guys, my computer froze for a second. So when you get to the lab segment, you see spring strength, mass, unstretched length, resting position, movable line, period trace, velocity, acceleration. So here what we want to measure is the amount of stretch that occurs per load or mass added to the end. So what we want to keep constant, okay, is our spring strength. What we're going to change is the mass applied. Okay, so our independent variable, the variable that we are changing, is going to be the mass. You can see this toolbar up here. You can scroll from left to right to make it larger and smaller. Okay, and spring strength, again, you want to keep it constant. But up to you what exact strength is going to be. You're going to solve for that. So I'm going to leave it up to you. But I do suggest that those in your group stick to the same spring strength so that you have someone to kind of check your work off of and discuss whether your results make sense. Okay, so I'm going to keep my spring strength 3 notches from the left. I'm going to increase my mass at even intervals. Okay, so I'm going to start with 50 grams. You see when you change 50 grams on the actual dial, the mass that's attached changes. Okay, to get the spring to stop oscillating, you click the stop sign. We're interested here in the stretch length. So in the toolbar on the upper right corner, you're going to click unstretched length. We're going to click movable line. To help us determine how much the spring has stretched. You're going to use the ruler to mark that stretch distance. Okay, that ruler is measured in centimeters. We're going to convert to meters. Okay, so in the simulation, grams is given to us in, or mass is given to us in grams. Length is given to us in centimeters. We want kilograms and meters. Okay, so I'd measure my stretch distance here. Okay, and I'm going to record it in my data table on my document. Okay, I want my first position or starting point to be 0. So I have a mass of 0, the stretch of the spring is 0, so the force applied to the spring would be 0. when I add 50 grams, okay, aka 0.05 kilograms, the stretch is 2.3 centimeters, okay? To find the force, let's see if I can get my pen here. Yeah, there we go. To find the force applied by the spring, and this isn't going to work for me, is it? No. Let's see if I can do this. There we go. Okay, so free body diagram, right? To find the force applied by the spring, we're going to draw a free body diagram for the mass. This is just a reminder as to how to find that spring force or the restoring force. Okay, we know that the force of gravity is going to pull downward on the mass that's attached. Okay, so on the actual mass, we have the force of gravity acting, which pulls the mass down, right? Force of gravity is the object's mass times g, 9.8 meters per second squared. What's holding that mass up is the force of the spring, F sub s. The mass is not moving. So you know that those two must be equal to each other. When we sum the forces in the y using Newton's second law, we find that the sum of the forces are equal to 0 because there is no acceleration. So restoring force or the spring force, right? Those two terms are synonymous for each other. They mean the same thing. They are the two names for the same exact force. The spring force points up in the positive direction. The force of gravity points down in the negative direction. Okay, and the sum of those forces are equal to 0. Again, just deriving that equation that we've used previously in class before spring break. So here, for a vertical spring mass system, the spring force is equal to the force of gravity of the mass that's applied, okay, or the load that's applied. So we're going to take the mass, which for my first example would be 0.05 kilograms, and we're going to multiply by 9.8 meters per second squared. And we get that the force of the spring, or the restoring force, must be equal to 0.49 newtons. Okay, so you want our first reference point to be 0, 0. We're going to increase the mass at a consistent rate. So I'm going to go from 50 grams to 100. Okay, I'll again measure the displacement. Once I find the displacement, I will record that in my data table for 100 grams or 0.1 kilograms. I'll then take 0.1 and multiply by 9.8 to get the restoring force. You're going to repeat that for 6 to 8 different masses. Once you've recorded that for 6 to 8 different masses, you're going to take your data and you're going to Control-C copy and Control-V paste your data into the Hooke's Law Google Sheet that's posted in Classroom. You're going to post that table next to vertical spring mass system. You notice here that there are 2 columns. We're going to graph stretch distance versus restoring force. So our stretch distance, right, is the second column here. You're going to copy and paste it under your X value, your displacement. Restoring force, F sub S, is the third column. You're going to copy and paste your data into that third column. Once your data is in the data table, you can delete that table. To better analyze the relationship between stretch distance and load or force applied, we're going to graph force versus stretch. Force versus stretch. So if we're graphing force versus stretch, think about which axes force and stretch should be located on. So you know for velocity versus time, right? Velocity is on our y-axis and time is on our x-axis. Okay, so if we're graphing force versus stretch, we want force on the y-axis and stretch on the x-axis. Okay, so we're going to go to Insert, Chart. Now it's been a while since we've graphed. So you're going to go to Insert, Chart. A nice pre-populated graph will pop up. We just need to specify it to make it a little bit more specific, right? We need to make sure we have a title, axis labels, intervals, okay, and a trend line. So the title, we have force in newtons versus X. We're going to make that a little bit more specific. We have force in newtons versus stretch. We want to specify what kind of system this is. So we're going to use our title over here to help us out. We want vertical spring mass system. Okay, force versus stretch. We see that on our y-axis, we have force in newtons. On our x, we have stretch in meters. This is exactly what we want. So it looks good, no need to change it there. In our chart editor, right, we see that we want to make sure that this is a scatter chart. The x-axis should say stretch in meters. The y-axis or series should say force in newtons. To customize our graph a little bit more, we want to make sure that our data points are legible, etc. You're going to go to series, trend line. Okay, so thinking about what Hooke's law states, right? Force is proportional to load applied. What kind of trend line do you think our graph should show? The force and stretch are proportional. Okay, if you're not sure, you can also try out the different trend lines. Okay, even when we try out a number of trend lines like a polynomial, logarithmic, power series, okay, they basically denote a linear trend line. If you looked at the equation, it actually gave you the equation y equals mx plus b. Because the two variables are proportional, as one changes, the change in the other variable is directly proportional. When you graph that, you're going to get a linear trend line that follows the equation y equals mx plus b. We want to show that equation on your graph. Okay, so we have a linear trend line label. We're going to use equation. That's going to give us the equation of this line in slope y-intercept form. Okay, last step for my graph, I'm just going to add a couple more grid lines here. So under customize, I'm going to go to grid lines. My camera's in the way. Let's see if I can move it. No, now I'm really large on the screen. I'm going to have to exit out here. Okay, so for grid lines, you're going to want to add a few more grid lines. So for force, we're going up by 1. Let's add a minor grid line so that we go up by 0.5 newtons instead. For our x-axis, we're going up by 0.05 centimeters. I'm just going to go under grid lines, change this to horizontal axis. I'm going to add one more minor grid line so that we go up by 0.25 or 0.025 meters. Okay, so we have this graph here, okay, with a linear trend line, force versus stretch. This equation here is y equals mx plus b. Right, so that equation would be y, aka this line, equals 18x plus 0.0357. So thinking about y-intercept form, right? Y equals mx plus b. M is the slope, right? This is the y-intercept. Our y-intercept is basically 0. That makes sense. This slope here, m, we know that slope is rise over run. Our rise is force. Our run is stretch. So let's think about that. What is the restoring force divided by the stretch? Thinking about Hooke's law, if we divide both sides by x, we find the spring constant. So the slope of that line is the spring constant, or the rigidness of that spring. So my spring constant here, K, is 18 newtons per meter. Okay, your value for K is going to change based on your simulation. So you're going to have different values for K based on the strength that you choose. Once you have your data table filled out, you're going to answer the guiding questions the best that you can. Okay, so answer 1 through 5 the best that you can. On Thursday, we will approach, after our discussion on Wednesday, we will approach how we're going to do part 2 with our rubber band. Okay. All right, so if you have any issues, you know where to find me. And I will see you guys tomorrow at our class meet.